Hello, my name is Carla, and I'm going to present some results we have on the leaf spanning arborescences in directed acyclic graphs. This is a joint work with Cristina Fernandes. So, a directed acyclic graph is a graph with no oriented cycles. A tree rooted at some vertex x, oriented in such a way that every vertex has, except for x, has in degree 1, is called an arborescence. Vertices without degree 0 in this arborescence are called leaves. An arborescence is spanning if it reaches all vertices of the digraph. It's important to notice that not all digraphs contain a spanning arborescence. For instance, this one. Maybe if we use this as a root, we would never reach this other vertex here. That's why in this problem we consider a rooted digraph. So we know there is a vertex R, from which there is a path to every other vertex. Now the problem is, given a rooted digraph, we want to find the spanning arborescence with the maximum number of leaves. This problem is of course NP-hard, even for directed acyclic graphs. It's also max SNP-hard, even for DAGs. There is a 92 approximation algorithm for it, which is in fact a 24 approximation if the digraph has no diagonals, which is in a structure like this one. And there is a 2 approximation for DAGs. So what we did in this paper was to present a 3.5 approximation for the problem, considering DAGs. Our algorithm is quite simple, it's a greedy one. We start with all vertices unmarked, and we expand the forest, marking vertices. We always expand vertices of out degree 0, like this one. And when we expand it, we mark all of its out neighbors that are unmarked. So in this case, we would mark all of these 4 vertices here. Now if we choose to expand these other vertex here, we would mark these 3 out neighbors. Of course, this one is also one of its out neighbors, but if we expand it like this, we wouldn't have an arborescence. So in the first phase of our algorithm, we greatly expand vertices with at least 3 unmarked neighbors. The forest generated by this phase is called F1. In this forest, we have 25 vertices in non-trivial components, and we have 3 non-trivial components. The second phase is the maximum 2 expansion phase. We expand here the maximum number of vertices with 2 unmarked neighbors. The forest generated here is called F2. Now we have 32 vertices in non-trivial components and 4 non-trivial components. The last phase is the connection phase, where we greedily connect vertices with 1 unmarked out neighbor. So this phase generates only 1 non-trivial component, which is the final arborescence. I think it's important to notice that this phase is quite difficult to be performed in any directed graph. The fact that this is a rooted directed acyclic graph guarantees that this phase will perform correctly. So the previous 2 approximations that existed for this problem was quite similar to ours. They started with unmarked vertices, and they greatly expand vertices with at least 2 unmarked out neighbors, and then finally connect them in the last phase. The news here is that we greatly expand vertices with at least 3 unmarked out neighbors, and then we expand the maximum number of vertices with 2 unmarked out neighbors. So let me explain how this phase works. Given the forest F1 generated by the first phase of our algorithm, we notice that there may be several 2 expansions that can be performed here. So we create an auxiliary graph where we put the vertices that will be marked here. So these vertices will be in this auxiliary graph. And we put an edge between 2 vertices when there is a vertex that can be expanded and to mark those 2. So each edge in this graph represents a 2 expansion for us. And the maximum matching in this graph gives us the maximum amount of 2 expansions that can be performed over F1. So I'll give you an idea of how we calculate the performance ratio for this algorithm. So for each of the 2 forests that we create during the algorithm, we call Ni the number of vertices in non-trivial components of Fi, and Ki is the number of non-trivial components also of forest Fi. Remember that T is the final arborescence returned by the algorithm. After the first expansion phase, forest F1 contains some non-trivial components, K1 non-trivial components, and in each of them, all the vertices have alt-degree at least 3. That's why we know that the number of leaves in each of these non-trivial components is at least twice the number of vertices there, plus 1 over 3. And if we sum these over all the non-trivial components of F1, we have this number here, which can be simplified to this expression. Now, to create forest F2, we may lose some of these leaves. Notice that the number of components of each forest is the number of non-trivial components plus the number of trivial components. So the difference on the number of components over 2 is the number of leaves lost from F1 to F2. So the number of leaves in F2 is at least what we had in F1 minus the number of leaves we just lost, which can be simplified to this expression. Now, the number of leaves lost from F2 to T is the difference on the number of components, because T has only one component. So the number of leaves our algorithm creates is at least this expression here, which involves the number of vertices in non-trivial components and the number of non-trivial components. Now that we have this lower bound on the number of leaves that our algorithm creates, we want to relate this with the number of leaves of any optimal solution. So what we need now is to find an upper bound on the optimal number of leaves, which is also expressed using the number of vertices in non-trivial components and the number of non-trivial components. Of course, we know that there cannot be more leaves than the number of vertices themselves, but notice that the number of vertices can be written as the number of vertices in non-trivial components plus the number of vertices in trivial components. If Li is the set of vertices which are in trivial components of the forest Fi and are leaves of an optimal forest, then we know that the optimal solution cannot have more than the number of vertices in non-trivial components plus this number Li of vertices that are leaves in trivial components. Now that we improve this part of the expression, we will improve this part here. And the idea is to assign a witness to some vertices. A witness is a vertex from a non-trivial component of a forest, Fi, which is internal in an optimal solution, so they cannot be leaves. So if omega is the amount of witnesses we have, we cannot have more than this number of leaves in any optimal solution. Now let Ri be the set of roots of the non-trivial arborescence of Fi. So notice that the size of Ri is Ki. We assign witness to this set of vertices here. For forest F2, we can assign a distinct witnesses to each vertex in this set. So the number of witnesses is exactly the size of this set. This allows us to find this upper bound here. This was already an upper bound for the two approximation algorithm. For forest F1, things are a bit more complicated because some of these vertices may share the same witness. However, these vertices are those that can be marked in the second expansion phase. So the rough idea here is that if they have the same witness, there is an edge between them in the multigraph. Therefore, we can relate the number of witnesses with the size of the maximum matching. And it was because of this analysis here that we needed the maximum matching in the second phase. This allowed us to find this new upper bound here. Now with these two upper bounds, which are written using the number of vertices in non-trivial components and the number of non-trivial components, we can relate it with the lower bound we found before to show that the number of leaves found by our algorithm is at least 2/3 of the optimal solution. And this ratio is tight for our algorithm, as we can see in this example here. So it could start expanding this vertex here, and we would have as leaves these vertices, and this one, of course. But as we can see, an optimal solution here would be to expand this vertex, and we would have all of these as leaves. So this is an ongoing work. we are trying to improve this approximation ratio. We are now analyzing a version which starts expanding vertices of alt degree 4, which is a natural improvement on our algorithm. So the complicated thing here is that we have to solve a 3D matching to find the 3 and 2 expansions that we have to perform in the next phase. And this problem is not polynomial as the maximum matching. However, the instance that we create in this phase is quite specific, and we really believe we can improve the approximation ratio now. Of course, it would be really nice to improve the 92 approximation we have for any rooted line graph. But as I mentioned before, it's very hard to guarantee the connection phase, so we would have to come up with a totally new idea here. Even if we could improve the 24 approximation when there is no DAGs, I think it would also be a really nice result. And there is a true approximation for graphs. Okay, so we have no orientation now. The connection phase is simpler to be obtained. But this is a 20-year-old result, which would be really interesting to improve. And that's it. Thank you very much for your attention.
So, I have a question.
So, seems that Guilherme has a question.
Cristina, if I understood correctly, Carla mentioned that you know how to improve some approximation factor. And I would like to know which is the factor you can improve, and if it's possible to give some idea on what has changed since the result you had in the talk for the new approximation factor.
Hello, so I'm answering the questions. Can you hear me?
Yes.
Okay, so I'm answering the questions about this talk. Sorry for the problem in the beginning, but I hope you could understand. So Guilherme, yes, we are trying to push this strategy, as Carla mentioned at the end of the talk. So we first tried to see what we could do about the 3D matching, and then what happens is that the algorithms for the 3D matchings, the approximations, because we don't have a polynomial time algorithm for maximum three-dimensional matching, but the approximations for three-dimensional matchings use independent set, maximum independent set. So we managed to use this to tune the approximation for maximum independent set to improve this phase. So we do greatly expand any vertices that have out degree at least 4, and then we apply a tuned version of the best approximations for this independent set algorithm that is related to the maximum 3D matching. And then we believe we'll achieve a slightly better approximation. So we believe we can get 7/5 approximation. It's not so straightforward. It needs more work, but we are on the way, I think, to get a 7/5 approximation, which is better than the 3/2.
Okay, I see. So you already managed to expand for the guys with alt degree 4.
Yeah? Yes, the hard part is every time you allow only larger expansions in the greedy phase, you get a better number of leaves. But the problem is what you do afterwards with the rest to get a connected thing.
Okay, thanks a lot, please.
Thank you,
You're welcome.
Are there any questions, please? More questions to Cristina?
Okay, I have a question
Fabrice has a question.
So I should have a question pertaining to the problem in general and like directed acyclical graphs. So you mentioned in the beginning of the presentation that the problem is NP hard, right? Even for directed acyclical graphs. Is there any known characterization for subclasses of directed acyclical graphs where the problem is tractable?
Not that I recall. Not that I recall. We have proved that it's still even max as NP hard, so it's not, it's unlikely that there is a PTAS. But for subclasses, I don't know. I would have to check. I don't know by heart if there are easier cases than directed acyclic graphs.
Thank you.
Thank you.
Are there any questions? More questions? It seems okay. It seems not. Okay, thank you, Cristina and Carla. It was a nice talk.